Okay, so ladies and gentlemen, welcome to our second online lecture of this Math 427. So in today's lecture, we'll try to go through this Bayesian estimation. So what is that? So actually, this is another aspect of parameter estimation. So just recall what we have done before. So in previous session, so we try to consider the case that, so let's say you got a random variable, okay, whenever it is a came severity or came frequency, and then it follows certain distribution, okay, whenever Poisson, gamma, exponential, whatever, and then with some unknown parameter, okay, and then our goal is we try to estimate this theta, right? Now, and then at that time, so we try to assume that, so this theta is a fixed parameter, so that means it's just a constant, but just we don't know what is the value, okay, and then to estimate this, so then we try to use the sample data and try to do the estimation. Okay, so then this is what we do before. Okay, but now under this Bayesian estimation, so we will try to consider a slightly different setup. So again, we assume that so the random variable S follows certain distribution with the parameter theta. But this time, instead of assuming that the theta is constant, so we will assume that so this theta itself is also a random variable. Okay, so then this is a setup in the Bayesian estimation. Now, then one question perhaps most of you will ask, so how come your theta can be a kind of random variable? Why do we assume that? What is that for? So in fact, actually, so this will be related to one scenario that often appear in the insurance problem. Now, so let me talk about that in details. Okay. Now, so let's suppose I concede. So let's suppose I got a particular person. Okay, and here let's say he passed the driving test. Okay, and then he got the new driving license. And then of course after getting this new driving license, then one way of celebrating it is you try to buy a new car, isn't it? Okay, so this is the proper way of celebrate this achievement, isn't it? Now, and then of course in order to buy the car and drive it on the street, then of course you have to buy an insurance. Okay, so here then he go to the insurance company and try to pay some money and then buy an insurance. Okay, and of course it can be a full multi-vehicle insurance or maybe just a third-party liability insurance, which is required by law. Okay, now and then here then what will be the problem there? Now, so of course when this new driver buy this insurance, then of course the insurance company will need to calculate the premium charged to this new driver. Okay, now and then as we said before, so this premium will depends on two things. Okay, so one will be the number of trouble caused by the driver, right? Which is your claim frequency. And then of course another one will be the SI, right? So which is the loss amount in each accident. Okay, so then of course these are the two things, okay, that they have to the insurance company need to estimate. Okay, now and then here let us first just focus on the claim frequency first. Okay, now and then in order to get the distribution of the n, so first of all you try to assume so what kind of distribution that the n will follow, right? And then of course in most of the cases, so we will assume that this claim frequency will follow the Poisson distribution, isn't it? Because this is a useful distribution that used to describe how many accidents that happen within a certain period of time. Okay, now and then here, as we know, so given the Poisson distribution, so it will associate with a parameter lambda. Okay, and here remember in the Poisson distribution, so this lambda will represent the average or more formally expected value of n. Okay, so which means well, it is the average number of accidents caused by the driver, right? Okay, and because of that, so of course, so this average number definitely will depend on what the quality of the driver. Okay, and then of course our common belief is, so if the driver is a good driver, responsible driver, then definitely this lambda will be lower. Okay, and of course if this guy is a troublemaker, which is a very bad driver, then definitely he will cause a lot of accidents. So that means the lambda will appear to be large. Okay, now and then of course in order to predict the true distribution of the n, then of course the company need to examine so what is the values of this lambda. So that means he need to know what is the quality of the driver, whether this driver is a good driver or a kind of troublemaker. Now of course in order to get this, then what the insurance can do is then they try to look at the track record of this driver, right? So in particular here, then they will try to look at the driving experience of this driver and try to see, okay, so in the past few years, so will this driver case how many accidents caused by this driver. But here, so this approach is only useful if this driver is experienced driver who drive for a couple of years. Okay, so that you have some actual record that you can check. But now in this situation, so this guy is a new driver. Okay, so meaning that he has no driving experience. Okay, so in that cases, so the insurance company cannot really assess to true quality of the driver. And perhaps the best that they can know is, so they only know that this driver is only taken from a population which contain a good driver and bad driver, isn't it? And then this driver is only a particular person that coming from this population. Okay, but you don't know whether it come from a group of the good driver or come from a group of the bad driver. Okay, and then because of that, so they don't know what is the quality of the driver. Okay, so there is an uncertainty of that. And then of course because of that, so that means that they don't know the true value of the lambda, or perhaps given this, so actually this lambda will now become a random variable. Okay, that means with some probability, so this lambda happen to be small if the driver is a good driver, or with some probability it may be equal to the large value if the driver is a bad driver. Okay, so in that cases, so we will encounter the situation that so your lambda, your parameter is a random variable instead. Okay, so that's why, okay, this is right. So why do we assume the parameter is a random variable? Okay, so here then this is the basic setup of this Bayesian estimation, which your parameter actually is a random variable. Okay, now then once we have this idea in our mind, then we try to continue our example. Okay, now so as I have said, so initially, so the insurance company need to estimate the distribution of n, right? Okay, now then given that, okay, so the number is a random variable. Okay, so they still need to estimate the distribution of n in order to calculate this p-minimum. Okay, now then of course in order to do that, so then what they do is they try to make some guess. Okay, make some guess on the values of lambda. Okay, so that given this guess, then we try to obtain the distribution of n. Okay, now and then here to facilitate the analysis, so let us try to assume that so we only have two type of driver, either good or bad. Okay, so that your lambda can only have two possible value, so either lambda good or lambda bad. And as I said before, so if this driver is good, then the lambda should be smaller, so that we will assume that so like lambda good less than lambda bad. Okay, now and then initially, so when the insurance company has no information about the client, so what they do is then they will try to make a guess on these values of lambda. Okay, so based on the information that he know, and perhaps here then what they can do is, so let's assume, okay, so in this population, so he know that, okay, so you have P of the driver which is good, and then 1 minus P of the driver is bad. Okay, and then here knowing that so this person is coming from this population, then here then he can conjecture that so with probability P this guy is a good driver, so meaning that the lambda will be equal to lambda good, and then with probability 1 minus P, so so the lambda will be equal to lambda bad. Okay, so here then this distribution, okay, will be the company initial guess on the value of lambda, okay, based on what he knows so far, okay, just based on some public information or whatever. Okay, so here then this probability distribution will be what we call pilot distribution of this lambda, which represent the company belief on the true value of the parameter without any direct or indirect observation on the values of this n. That means I don't observe any information about this client. Okay, and then here, so we will denote this pilot distribution by this pi lambda. Okay, so which is the distribution of probability distribution of lambda. Of the parameter. Okay, now and then so given this pilot distribution, then now you can try to given this guess, then you try to figure out the distribution of your okay, of your original random variable n, which is your number of accident case by the driver. Okay, now and then here and then to do this, so so we know, okay, so the n follow the Poisson distribution, right? And then with some parameter lambda. Okay, and then here in order to get this probability distribution, okay, that is the probability that so this guy will case exactly n accident. Okay, now and then of course in order to get this probability, then you have to first get the values of the lambda. Then here, given this uncertainty of the lambda, then what you can do is you can try to compute this probability using the law of total probability. That is, you try to consider all possible values of the lambda. Okay, and then multiply by the corresponding likelihood that the lambda equal to particular value. Okay, and then here, so so given, okay, you know this probability, and then you also know that, okay, so let's say the n follow positive distribution. So once the lambda is fixed, so you can also calculate this two probability. Okay, so that then you can obtain the distribution of your original random variable n. Okay, so here the distribution of n which you obtain from this initial guess, then this is what we call marginal distribution. Okay, of the n. Alright, so which is what defined as the distribution of n, okay, determined based on the pilot distribution of lambda, so which is your initial guess. Okay, so then here, then this will be the first step of the Bayesian estimation. Okay, now but of course here the story will not be just as simple as that. Okay, of course initially, so when you don't have any information about this client, of course, and this one will be your best guess on the distribution of n, isn't it? Now so here let us try to think about think about this scenario. Okay, so let's suppose, so after 1 year, okay, now and then this client try to renew the insurance. Okay, now then of course the insurance company will try to answer the same question on the distribution of n, isn't it? Now but the situation will be something different from time 0. Okay, because now at time 0, so you don't have any information about the client. Okay, but at time 1, all right, so actually you will have some new observation. In particular here, so so what you know now is the n1. Okay, is what is the actual number of accident case by the driver in the first year. Okay, I mean, for example, first period or first year. Okay, never mind. Okay, now so which is this period. Okay, now and then of course here based on this new information, so actually this company can have a better guess on the quality of the driver. Okay, so for example here, let's say if I find that okay, so the NI is equal to 0. Okay, so let's say no accident case by this driver. Okay, then of course for the company point of view, then they will think so this driver will be likely to be good, isn't it? The reason here is because if this driver is good, okay, then the probability that of casing no accident should be relatively larger. So let's say 0.9. Okay, and maybe for bad driver that will be 0. Just make it a little bit extreme. So let's say 0.2. Okay, and then he had and then he will case trouble with probability 0.1 and 0.8. Okay, now and then let's say if this guy does not case any accident in the past year. Okay, and here given this analysis, so it looks like that. So then this one is likely to be good driver, isn't it? Because what? So because if this guy is a bad driver, actually it will have a very small likelihood of casing no accident, right? Okay, but here because this is something actually you observe. Okay, then of course just like the maximum likelihood method, then you will have the tendency to believe that this guy is a good driver. So in that cases, so initially, so maybe initially, okay, so you may think, okay, so this guy can be a good driver or bad driver. But now after observing NI equals 0, then you have more tendency to believe this guy is a good driver, isn't it? So then this will be what your new guess on the distribution of the quality of driver, right? Okay, and of course here, let's say if you find that this guy case some accident, so let's say n1 equal to 2. Okay, then of course in that cases, because according to this observation, so as we know, so only the bad driver will have a larger likelihood of casing accident, right? So in that cases, so he will believe that, so it will have some more tendency that this driver is a bad driver, isn't it? So that this will be what his new guess, okay, on the quality of the driver. Okay, so here using this new observation, so now he can try to do this, try to update his guess, okay, on the quality of the driver. So then this process is what we call information updating. Okay, so which is one of the important process of the Bayesian estimation, which is given this new observation, okay, which is your new sample data, then you try to update the distribution of your unknown parameter lambda. Okay, now so here, okay, so then this is the basic idea of this information update. But mathematically, then how do we do that? Okay, now so here let's assume, okay, so in the last period, so you are given that, so this guy case n, so has a n1 claim, okay, which means n equal to n1. Okay, now so here then given this new observation, so how do you update the distribution of the lambda? So again, we will focus on the case that we only have two possible values of lambda. Okay, now so then how do we do this updating there? Okay, now so here to get this new distribution, so again we are seeking for the probability that lambda equal to a particular value, but this time so this probability will now become a conditional probability, okay, because this will be what, a new given event. Okay, now so here in order to get this conditional probability, so we can try to use the definition of conditional probability, so which is equal to that. Okay, and then here using the multiplication rule, okay, so then you can break down this numerator into this. Okay, so just remember p probability that a and b can be written as the probability that a given b multiplied by probability that b happen, right? Okay, so then this is what you get for the numerator. And then for the denominator, you are asking for the probability that n equal to n1. So actually this is just a marginal distribution, something that you can compute using the law of total probability. Okay, so here then that will be what the formula that you can use to get this new distribution of the lambda. So given that you know some actual value of this n. Okay, and of course this formula is commonly known as the Bayes rule. Okay, now and then here, so this is the probability that lambda equal to lambda goods. Okay, and of course for the case for the probability that's okay the lambda equal to the lambda bad. Okay, so actually you can apply the same Bayesian law, okay, and do the estimation. Or because in our cases, so we only have two possible values, and we know sum to probability equal to 1. So that here, given that you know the probability that lambda equal to lambda good, then you can just try to get the probability for the lambda bad. Okay, so by using the sum to probability equal to 1. Okay, so that is you try to do this by 1 minus the probability that lambda equal to lambda goods. Okay, so then here given this observation, so then you can now obtain this new distribution of the lambda. Okay, using this based on this new observation. Okay, so here then this new probability distribution, okay, so which is in forms of the conditional expectation. So this will be what we call posterior distribution of the parameter lambda. Okay, so which is the updated distribution of lambda obtained based on the new observation observed. Okay, so then this is the posterior distribution. Now and then of course given this new posterior distribution, now then you can try to make a new prediction on the distribution of your n. Okay, now so here, okay, so given this new distribution of the lambda, then you can now try to get the new distribution of the number of claims. Okay, so let's let it to be n prime, okay, or maybe just the n if you like. Okay, so here then you can get this they can now use the conditional probability and use the law of total probability and try to do the job. Okay, so basically we essentially use the same formula, except that, okay, so we will try to use the most updated distribution of the lambda and calculate this new distribution. Okay, so here so you will get the new distribution of the n. Okay, and then here then this new distribution of n, which is you calculate based on the updated distribution of the lambda, is what we call predictive distribution of n. Okay, so here, okay, then this is what the process of this Bayesian estimation. Okay, so just a quick summary here. So actually the Bayesian estimation is carried out as follows. Okay, so here we let the s, okay, to be a random variable with some be a random variable which has certain distribution involving the parameter theta. Okay, and here of course this theta in general can be a single parameter or it can be a multiple parameter, just like the log, normal, gamma, also like that. Okay, and here, okay, so we assume that, okay, so the lambda, so this theta is a random variable. Okay, now and then here okay, when we try to estimate the lambda under this Bayesian estimation. Okay, so first of all, initially, okay, so which you don't have any information on this observation of S. Okay, now then remember, in the initial stage of your Bayesian analysis, so you first try to make a initial guess on the lambda, right? On the theta. Okay, so that means, okay, so you first try to assign a probability distribution on this parameter. Okay, so just like what we did in this earlier example. Okay, so you first try to make an initial guess. Okay, so based on your knowledge that you know. Okay, so then this initial guess will be what we call pilot distribution. Okay, and then of course given this, okay, so you can try to calculate the corresponding distribution of S. Okay, then here, then this distribution, okay, so which you calculate based on the initial guess, so will be what we call marginal distribution of S. Okay, and then here, formally to calculate this, so you try to make use of this law of total probability. Okay, so remember, so this one is roughly represent the probability that S equal to S, given that, okay, you know the values of lambda. Okay, so that means, so you try to consider all possible values of the theta. Okay, and then you estimate this conditional probability, and then you multiply by the likelihood that, so the theta take a particular value, and then you sum up all this possibility. Okay, and this is how do you get your marginal how do you get the distribution of S, so which is what we call the marginal distribution. Okay, and then here this formula that will work for S is a discrete random variable or maybe continuous random variable. Okay, so of course if it is discrete random variable, then this FSS will be just the probability S equal to S. Okay, and then of course if it is continuous random variable, then this one is just a PDF. Okay, and this one also a PDF as well. Okay, now so here then this is the marginal distribution. Alright, so then this is what our initial assessment on the values of the theta and also the distribution of the S. Okay, now and then of course sometimes after, okay, so let's say some future time. Okay, now then let's say the time has passed certain period. Okay, and then you now arrive at certain period in future. Okay, and then of course given this, then you can now have some observation on the actual value of this S, isn't it? Okay, now and then here let's assume that, okay, you observe that So in the past period, so the s is equal to a small s. So this is your actual observation. On s. Okay, so which you can regard as a sample data. Of course, in general, so it can be you can have a multiple observation as well. Okay, so it is also fine as well. Okay, and here, so given that, okay, you have this new observation, so which is your sample data from S, then now you can try to make use of this and do the information updating. Okay, so to remember to do that, so we try to use the Bayes rule and do the job, isn't it? So here, then this new distribution of the theta can be given that, okay, you know the s equal to s, okay, then can be computed using this Bayes rule. Okay, so which is exactly which is exactly same as this. Okay, so which is the one that you see here. Okay, so here then this new distribution is what we call is what we call the posterior distribution. Okay. Okay, and then of course as a result, so given this new distribution, so your distribution of S will also change as well. And then here, using the updated distribution of theta, okay, so which is your posterior distribution, then now you can try to estimate your distribution of S, okay, using this formula. Okay, so you just replace the pi theta by the updated gas. Okay, and you get the new distribution. Okay, so here, okay, then this distribution is what we call the predictive distribution, isn't it? And then so formally I will denote it by this notation. So which is what the new distribution of S, given that you know some data of S in the past. Okay, so here then basically, so this is the whole procedure of this Bayesian estimation. First of all, you have the initial guess on that. Okay, and then in future, so you try to update this two distribution using the sample data that you get, and then together with the Bayes rule. Okay, so then basically this is the idea of this Bayesian estimation. So let's we are going to show you some numerical example about this Bayesian estimation. So here let's take a look on this example 33. So this example is just similar the example that I proposed before. Okay, so here we consider a problem faced by the insurance company. So that is so let's say we have a client who is just getting the new driving license, and then he want to buy a motor vehicle insurance. Okay, and then as I have said before, because this is a new driver, so that means this insurance company does not really know the quality of this driver. So meaning that so he don't know whether this driver is a good driver or the bad driver. Okay, and then here in this example, so we will try to demonstrate so how would the insurance company estimate the claim frequency based on the information that he gets at different time using this basic analysis. Okay, so here then this is the basic setup. So just like what we did before, so we assume that there are only two types of driver, either good driver or bad driver. Okay, and then depending on the quality of the driver, so we assume that the N will follow different distribution. Okay, so let's say if the driver is good, so you can see, so there is a huge probability that he does not cause any accident, and just have very small chance that it will cause the accident. Okay, and then for the bad driver, so it has a slightly higher probability of causing trouble. Okay, so then this is the configuration of our setup. Okay, now and then as I have said, so initially, so this insurance company does not have any information about the quality of the driver. So then to estimate the N initially, so what they do is then they will first have an initial guess on this quality of the driver. And then here, let's assume that so we have 50% chance that the driver is good, and then with 50% chance the driver is bad. Okay, so then this will be our initial guess. Okay, now and here what I'm going to do is, so given this initial guess and also his prediction on the distribution of N for different types of the driver, then what I want you to do is, first of all, just use that to derive the distribution of N, okay, for this new car. Okay, and then here to do that, so actually it's not that difficult. So given the initial guess, so remember you can try to calculate this distribution of N through the law of total probability. Okay, so you just fix the type of the driver and then you calculate this distribution, this probability. Okay, and here you only have two types of driver, so that this probability will be just sum of these two things. Okay, now and then here so for example, let's say if you want to calculate the probability that N equal to 0. Okay, now and then here then you use the law of total probability and decompose it into two terms like that. Okay, now so first of all for this so initially, okay, so they think that this driver, okay, is either good or bad with 50% probability, right? So meaning that each of these will be just equal to 0.5. And then so how about the first two probability there? Now so here, if the driver is good, then the probability that N equals 0 will be equal to 0.9, isn't it? Okay, so you can just go back to page 141 and check this number out. Okay, so which is this one. Okay, so which is this one. Okay, so good driver, then the probability that N equal to 0 will be 0.9. Okay, and then similarly for bad driver, then this probability will be 0.6. Okay, then here then you just sum them up, then you will get the 0.75. Okay, so which is the number that you get over there. Okay, and similarly you can also do the same calculation for the other three probability that N equal to 1, probability that N equal to 2, and probability that N equal to 3. Then here then you will have this initial guess on the distribution of N based on your initial belief on the quality of the driver on the N. Okay, so here then actually, so this is how do we get the distribution of N through this parallel distribution. So actually it's not that difficult, right? Okay, now and then here let us try to move on, okay, from time 0 to 1. Okay, so remember under this basic estimation, so when there is new information arrive, and actually so the insurance company can use this information to update their guess on the quality of the driver. Okay, let's look here, let us consider this scenario. So let's suppose 1 year has passed already. Okay, and then here within this 1 year, then the insurance company will know what is the number of trouble caused by this driver in the past year. Okay, so let's call it N1. All right, so that will be the number of accident, okay, caused by this driver over this 1 year period. Okay, and then so he can use that, okay, to estimate the new distribution of the quality. Okay, now and then here so we consider two scenarios. So first of all, let's assume that. So let's say if we find that in the past 1 year, so there is no trouble caused by this driver. Okay, then of course intuitively, so according to what we have here, okay, because the good driver will have more tendency to cause low accident compared with the bad driver, right? So we expect that. So in that cases, so then the insurance company will have more tendency to believe that this driver is good, right? Okay, so meaning that we will expect, so this distribution will be something like, so it will have higher probability that this guy is a good driver, and then for bad driver, then that will be small. Okay, and then we also consider another scenario that, so the n1 greater or equal to 2. Okay, so in that cases, so that means this driver is a troublemaker. Okay, and here then that means and here, okay, according to this table, so we see, so only for bad driver it has a tendency to give a higher probability that of causing a lot of trouble. Okay, remember we are talking about probability that n greater or equal to 2. Okay, so for bad driver, so it has 0.18 probability causing this thing, right? But for good driver, it only 0.05 only. Okay, so the sum of these two. Okay, so here then given this, then the insurance company will think that this guy is a bad driver. So that in that cases, so we will expect, so he has more tendency to believe that this driver is bad. Okay, and then what I'm going to do is, so I want you to based on this observation, so we try to confirm this by deriving the corresponding positive distribution as well as the predictive distribution of n. Okay, and see what this looks like. Okay, now and then here let us try to do the calculation carefully. Okay, now so here so let us first consider the case n1 equal to 0. Okay, the last cases. Okay, now and then here, in order to get this to get this positive distribution, then you can try to use the Bayes rule. Okay, so how do we get that? Now so here, okay, our goal is we want to determine this conditional probability. So remember, according to the definition, so that will be equal to the probability that it is a good driver, okay, and then no accident divided by the probability that n equal to 0, right? Isn't it? And then this one will be equal to n equal to 0 given that it is a good driver. Okay, and then probability that good driver. And then the lower one is just a law of total probability. Okay, so here, okay, I'm not going to memorize that Bayes rule, okay, because it's so tedious. Okay, so I just use this sort of old-fashioned method, okay, to get this. Okay, and then here, then you just punch in the number. Okay, so let's say for this probability good or bad, then that will be 0.5. And then for this one, it will be 0.9. And then bad driver, it will be 0.6. Okay, so then after you punch in the number, then this will be basically what you get. Then you will find that this probability that this driver is good will now become 0.6. Okay, and then for bad driver, so the probability will be 0.4. Okay, so here, okay, then you can see, so initially I think that's okay, so this driver is equally good or bad. Okay, but now after I see that n equal to 0, so we can see that, so this insurance company has a tendency to believe that this driver is good, so that this probability is getting higher and the probability of bad driver will be lower. Okay, and then here if we try to, and then here given this given this posterior distribution, okay, then now you can also use that to obtain your predictive distribution, okay, of the n. So here to get this, so you can just calculate this as follow. Okay, so given that, okay, n1 equal to 0. and then that one equal to the probability that n equal to 0, and then you have a good driver. Okay, and this time, okay, so this probability will become 0.6. Okay, and then pass the probability there. Given this bad driver, and then probability that bad driver n equal to 0. Okay, and then equal to 0.4. Okay, and then for these two probabilities, so one is 0.9, one is 0.6, nothing changes. Okay, so here then if you compute this, then you will find that this will be 0.78. Okay, so which is the number that I show here. And similarly, you can also do the same thing for n equal to 1, equal to 2, n equal to 3. Okay, so here, okay, then to get this predicted distribution, so we just use the same approach before. Just we replace this probability, okay, by the updated probability based on the new observation. Okay, and then here, if you try to look at the number here, okay, so you can try to compare with the initial case. Okay, so remember this is your initial guess, and then this is your updated one. Okay, so you can see, so because the insurance company think that it is a good driver, right? So you can see, so it has a more tendency to believe that it will cause no accident, and then with smaller probability of causing trouble. See that? Okay, so here, okay, then this is how does the insurance company do the updating. Okay, and similarly, if you find, so let's say you find that okay, so you find that this driver case a lot of accident, so meaning that it is a troublemaker, right? Now, and then here, if you try to perform the same calculation, okay, then you will find that, so this probability is now becomes, so for good driver, so the chance will be only 21.74, but for bad driver, so it will be raised to 78%. Okay, so you can see, so the insurance company will have a larger tendency to believe that you are a bad driver. And then here, if you try to look at the distribution of bank as well, so you can see it will pay more weight, okay, on the probability that this guy will cause trouble. And then of course, as a result, then the premium will be increased. Okay, so here, okay, then this is the detailed calculation about how do we get this posterior distribution and the predicted distribution based on this new information. And then we can also see that the result that we get here is consistent with what we expect. Okay, so if low accident, so more bias on the good driver. If NI is large, meaning that it is a troublemaker, then more bias on the bad driver side. Okay, now, and then here, so then this is this example 33. Now, and then here, I also want to bring out one interesting remark about this example. So will be regarding the number of observation versus the posterior distribution. Okay, now, so here in the early example, so we see the insurance company can use what he observed to update the belief. Okay, and then in the early example, so we try to do the updating based on the observation in the past year. Okay, so meaning you only have one data. Okay, now and then here you can see, so even though this guy does not cause any accident. Okay, so here you can see from the calculation that it looks like that the insurance company does not 100% trust this guy is a good driver. Okay, so we can see that it only pays a slightly larger weight on the probability that this guy is a good driver, only 60%. But still, it has some tendency to believe that you may be a bad driver. I would say the reason here is because here, when they try to determine this posterior distribution, actually what they do is they will try to look at the likelihood that each type of the driver will cause the same event. Okay, and here actually from this table, so you can see, so actually the bad driver will also have 60% probability of causing no trouble. Okay, and then because of this, so actually the insurance company will still have some tendency to believe that this driver may be a bad driver, but just because of the luck, so he case no accident. Okay, so that's why so that's why you have this result. Okay, and of course here another possible reason is because we only have one data only. Okay, and definitely this data may not be strong enough to convince the insurance company to believe you are a good driver. Okay, then of course some people may probably say that. Okay, so let's say if you have more data, okay, to support to do the support. Okay, so the insurance company will change their mind, okay, and have more trust on the quality of the driver, meaning that it believe that the driver is good. Okay, so here let's suppose we have 5 years has passed and he find that so in the past 5 years he does not case any accident. Okay, now so here in that cases, okay, so if you try to compute the corresponding posterior distribution, so which you can do it using the base rule again. Okay, then you will find that so this probability will be equal to this. Okay, so here just let me explain a little bit. So how do you do this calculation? Now, so here, okay, so here your given event, okay, will be what? Will be n1 will be this n1, n2, n5 are all equal to 0. Okay, so meaning that okay, this will correspond to this event. Okay, now and then again to calculate this posterior distribution, so basically we use the same formula, except that here the event B will be equal to this complex event. Okay, and then here let's assume that so the number of claims in the past 5 years are independent to each other. Okay, so then this probability will be equal to 0.9 to the power 5. Okay, so for good driver. Okay, and then 0.6 to the power 5 will be for bad driver. And then based on this, so then this probability will be equal to that. Okay, so then this is how do you get this expression. Okay, so here then after some calculation, so you will find that so this probability that this driver is good will now raising to 88.36%. Okay, and for bad driver then there will be only 11.64%. Okay, so you can see compare with the case with only one data, okay, so which is 60 and 40, and now with more data that can support this driver is good, then you can see the insurance company has more confidence to believe that this driver is good. So you can see this probability raised to 88%. Okay, and why does it happen? So the reason here is so now if you try to look at each type of the driver and try to look at the likelihood that it can generate 5 COK in 5 consecutive years, and now for good driver, so this probability will become 0.9 to the power 5, so which is equal to 0.59049. Okay, and but for bad driver, so this probability actually is very, very small, only 7.7776%. Okay, so here you can see now for the bad driver, actually it have a very small likelihood that casing 5 COK in the past 5 years. Okay, so that's why here, so given this achievement, so it will has a larger tendency to believe so this is a good driver. Okay, because there's a huge differences in this probability. Okay, so here, okay, then this is just telling you how that this number of observation, okay, affects this posterior distribution, and according to what we get here, then it looks like that. So if you have more supportive information up to the good driver, then it looks like that. So this probability will be bias high. Okay, so then this is the example 33. Now then let's try to move on to some other example. Okay, and just have a very quick practice on this Bayesian estimation. Now, so in this example 34, so which is one exam problem from SOA. And in this problem, so we try to consider the insurance policy held by a company. Okay, and here, so it is given that so the losses that record in this insurance policy follow the Pareto distribution with alpha equal to 1 and then another parameter theta. Okay, so which is not long at this moment. Okay, now and here so here in this problem, so we assume that this theta will depends on different company, and then according to the historical data, so we find that so 50% of the insurance will have the theta equal to 1, and then another 50% of the insurance will have the theta equal to 3. Okay, so that means your theta will have two different possible value. Now and then let's suppose I try to pick a insurance policy randomly from this sample. Okay, so that means the theta will be either 1 or 3 with 50% probability. Okay, with 50% chance. Now and here so what I want to do is so I want to try to estimate this theta in this insurance policy. Okay, now and here of course without any information, then of course this is the best guess that I can have, isn't it? Now and here let's suppose I find that so the losses of this policy in the first year is 5. Okay, and here what we want to do is so given this observation, okay, so I want you to use this information and try to predict so what will be the probability that the losses in the second year will exceed 8. Okay, now so here then let us try to do the calculation. Okay, now so here so let me first draw the timeline. Okay, now so here you are given that so the losses in the first year is equal to 5, and then I want you to predict so over the second year, so what will be the probability that you have the losses greater than 8. Okay, so this is something that we want to figure out. Now and then first of all, in order to get this so in order to get this probability, now so remember these losses, okay, follow this Pareto distribution, and then which the value will depends on the theta. Okay, and remember the theta can be either 1 or 3. Okay, so here because of this, so to calculate this probability, then you need to divide it into 2 cases. Okay, so using the law of total probability, then you try to break it down into 2 parts. So here just one thing I want you to remind all of you that so when you calculate this probability, remember we should use the posterior distribution of theta. Okay, so do not use the parallel distribution. Okay, I mean this 50%, 50%. Okay, so the reason here is because here we try to do the prediction at time 1. Okay, and at that time so you have this information, and here when we do any prediction, so we'll try to use all the information available as much as possible. Okay, so here so when you calculate this probability, so you should use the posterior distribution. Okay, given that you have this observation. Is that okay? Now and then here let us try to calculate this 2 posterior distribution. Okay, now and then to get this, so here So let us start with the first one. Okay, so here the posterior distribution will be given by what? Pi1, and then given that s1 equal to 5. So this one is just equal to what? The probability that theta equal to 1 given that s1 equal to 5. Okay, and then here then you just use the base rule, okay, and then you can calculate this probability like this. Okay, so I guess I'm not going to go through the derivation of this formula again. Okay, it's just same as what we did before. Okay, now and then here for the pi1 and pi3, okay, so that is your polar distribution, so that will be equal to 50%, 50% respectively. Okay, now and then here so how about this conditional probability? Now so remember the S follow this distribution, isn't it? Okay, so with this PDF, and then here okay, so given the values of the theta, okay, so then this will be the probability. Okay, now of course this notation is a little bit informal because this is a continuous random variable, right? Okay, so here formally, so this should be a PDF. Okay, not really the probability. Okay, now anyway, so here, okay, then this is how do you get this posterior distribution? Then you will find that the number will be 16/43, and then once you get the posterior distribution for theta equal to 1, then of course you can also find the posterior distribution that's the probability that theta equal to 3. So of course either you can use the base rule to do the job, or maybe you use the sum to probability equal to 1, because in our cases, so the theta is just equal to either 1 or 3, right? Isn't it? Sorry, it's just either 1 equal to 3, so that the sum of this will be equal to 1. Okay, then here then that will be this posterior distribution. Okay, then after you have this posterior distribution, then now you can try to finish the job now. Okay, so then basically you can just calculate this probability using this formula. Okay, and then let's see. And then here, so for the posterior distribution, so this one equal to 16/43, and then this one will be 27/43. Okay, now and then here for this conditional probability, so given the PDF, so it will be just equal to what? The integral from h to infinity, and then your PDF, so which is your theta over s plus theta all square ds. Okay, and then here, okay, so you just put in the theta equal to 1 to get this, and then you put in theta equal to 3 and get the second one. Okay, so very simple. So here, okay, then this is what you get finally. Okay, then after you evaluate this two integral, which is very straightforward to do that, then you will find that the final probability will be only 21.25%. Okay, so here then this is how do we do your future prediction using this Bayesian estimation. Okay, so basically the idea is, so given this given the data available, okay, then what you do is, so you try to get the posterior distribution on your parameter. On your parameter theta. Okay, and then once you have that, then you use the law of total probability and try to finish the job. Okay, so hopefully it's very simple. Okay, now and then here, so then this is the example 34. Okay, now and then here let us try to look at this example 35. Okay, so actually this is again another example about this Bayesian estimation. Okay, now and then here in this example, so we consider a particular individual policy, and then for this individual policy, so you are given that there will be exactly 1 claim each year. Okay, and then so you are also given that, so for this claim event, so the loss amount of this single claim has a exponential distribution with this PDF. And here we will assume that, so the parameter lambda, okay, is random variable, and which has what the power distribution equal to this PDF. Okay, so that means that this lambda will be a continuous random variable with this PDF, and this lambda can take any value from 0 to infinity. Okay, now and then here, so this is our initial guess at time 0. Okay, and let's suppose after 1 year, so I realized that this came amount in last year is 5. Okay, which is something like that. Now, and then what I want you to do in this example is, so of course, given this data, then I can try to update the distribution of the lambda, right? Okay, but this time, what I want you to do is, so I want you to figure out, so what is the expected value of lambda? Okay, I mean the average value of this parameter. So here, so we want to compute the mean of this posterior distribution in the coming year, so which is something like this. Okay, now and then here, in order to do that, okay, so then let's just think about, okay, so how do you compute this expected value? Alright, then of course, in order to compute the expected value, then what you need to do is you need to load the PDF of lambda, right? Okay, now of course, here, this PDF, okay, definitely does not equal to this, because this is what a power distribution, okay, which is the initial guess on the distribution of the lambda without any information. But here, don't forget that, so we already have one information available. Okay, so here, what you should do is, so you should try to obtain the posterior distribution instead. Okay, now and then here, so how do we get this then? Okay, now so then to get this posterior distribution, okay, so which is given by this. Okay, then actually we just try to use the base rule to do the job. Okay, now remember this posterior distribution is just like what the probability that lambda equal to certain value given that s1 equal to 5, right? Isn't it? And then according to the definition, so that will be that definition of conditional probability, that will be equal to something like this. Okay, lambda and s1 equal to 5. Okay, and then probability that s1 equal to 5, isn't it? Okay, so here I use a slightly informal notation. Okay, and then here, so you can try to use this multiplication rule. And then the denominator so will be the law of total probability. Okay, so this is a power distribution. Okay, and then here, because this S1 is a continuous random variable, so we replace the F by the PDF. Okay, so here then this is what basically what you get in this formula. Okay, and here, okay, for the denominator, so you consider all possible values of lambda. And then here, because your lambda is running from 0 to infinity, right? So that this interval will be running from 0 to infinity as well. Okay, so that's why this is what you get. Okay, and then here, to do the computation, okay, so first of all, you can substitute the fx as well as the power distribution. Okay, now then so after a little bit algebra, then this is the expression that you have to handle. Okay, and then here, so it remains to compute this denominator. Okay, because a numerator you don't need to do anything, so you just need to evaluate the integral, okay, in the denominator. Now then what you can do is, so of course to evaluate this integral formally, you should try to use the integration by parts. Now but definitely here, okay, so with the power with the integral involving lambda to the power 2, so definitely we won't do the integration by parts twice. Really tedious, right? So instead, what I'm going to do is, so I will try to make use of the gamma function to help us. Okay, so remember, for gamma function, this will be equal to the integrals from 0 to infinity, and then t to the power alpha minus 1, and then exponential minus t dt, right? Okay, now and here, so actually this one is very similar to this integral. Okay, so here what I'm going to do is, so I will try to make use of the change of variable and try to transform this integral into the form which is similar to the gamma function. Okay, so to do that, then I will try to let this 6 lambda, okay, by a single variable. Let's call it y. Okay, then by applying this change of variable, then you can now transform this integral into the form like that. So which is what? Similar to this. Okay, now and then given this, so then this integral will be equal to gamma 3 by definition, isn't it? Now so here, okay, then this is what you get, and then to erase this gamma 3, remember we have this amazing identity. So the gamma alpha plus 1 equal to alpha gamma alpha, right? And then here you can put in. So using this, then you can get the gamma 3 will be equal to 2 times gamma 2. And then apply it once again. So this one equal to 2 times 1 gamma 1. And remember that gamma 1 equal to 1, right? So that this one will be equal to 2. Okay. And then given this, so then this is what you get. Okay. And then once you have this, then you can find that the posterior distribution will be 108 lambda squared times exponential to the power minus 6 lambda. Okay, then so see here, then that will be the new distribution of your lambda after you have the arrival of the information. Okay, so given this, okay, given this updated PDF, okay, of lambda, then now you can try to compute the expected value, isn't it? So here then so you just multiply the lambda by the updated PDF, and then you integrate from 0 to infinity. Okay, and then here so then this will be the integral that you need to handle. Then again, to erase this integral, so we just try to make use of the gamma function again. Okay, so again, then you apply the change of variable y equal to 6 lambda, so that this integral will be simplified into this, and then this integral will be just equal to gamma 4. Okay, and again, to erase this gamma 4, then you just apply this same same identity again. Okay, and try to get this, okay, to be equal to 3 factorial, which is equal to 6. Okay, and then after simplification, so you'll find that, so the answer will be 1/2. So here, then this is how do you get the expected value of the lambda via the Bayesian analysis. Okay, so I would say the idea is, so to compute the expected value, we need the PDF, but just we have the new information, so that means we should use the new PDF of the lambda. So that means you need the posterior distribution. Okay, then again, to get the posterior distribution, so you just use the Bayes rule and help you to finish the job. Okay, and here so then this is how do we do the part A. And then for part B, so what I want you to do is, so let's suppose if my K amount is raised to 10, okay, instead of 5. Okay, so what I want you to do is, so I want you to calculate this expected value again. Alright, and try to see, so how does it change. Okay, now and then here, by performing the similar calculation, so first of all, you will find that the posterior distribution will be equal to this number. Okay, and then once you get this posterior distribution, then you can just compute the expected value using this formula again. But just you replace this PDF by this PDF that you obtain here. Okay, and then again, so after some calculation, so you will find that the final answer will be 3/11. Okay, so you can try to do it at home as an exercise. Now, and then here, what I want you to do is, so I want you to compare this result for the case in A, which the loss is, so for the first one, the loss is 5. For the second one, the loss is 10. Okay, Now, so here you can see, so if you have the SI is larger, then you can see, so the expected value of the lambda happen to be smaller. Okay, why it is the case? The reason here is, so let us try to think about the meaning of the lambda. Okay, now so remember here in this problem, so the lambda is your parameter in your distribution of S. Okay, so remember S follow this distribution. This is exponential distribution, right? Isn't it? And then remember for exponential distribution, so the mean will be equal to 1 over lambda. Okay, so in other words, so this lambda actually is sort of indirectly represent the mean of the S. Okay, now and here intuitively, so if you was realize a big loss in the past, okay, then of course we will expect, so the mean of this S will be high, right? Okay, so meaning that if SI is large, S1 is large, then your estimation on the theta should be larger, right? So that means the lambda will be smaller. Okay, so in that cases, so if you consider expected value of the lambda, so you can see that for larger value of S1, so this number will be smaller. And of course, if your S1 is smaller, then that means the theta is likely to be small, then the lambda will be likely to be large. So that's why here you can see, so when you see the small losses, so the expected value will be higher. Okay, so here, okay, then this is just the explanation of these results that you obtain in this example 35. Okay, now then after this example, then let us try to look at one harder example. Okay, now so here in this example, so we consider this scenario. Okay, so here we will consider an insurance policy that cover a particular risk, and you are given that, first of all, the number of claims, okay, made in an insurance policy in 1 year has a Poisson distribution with a parameter lambda. Okay, so the M follow this Poisson distribution with parameter lambda. Okay, and again, just like the earlier cases, so here we will assume that, so this lambda will be a random variable. Okay, and then which has the gamma distribution with some parameter alpha and theta. Okay, but in this problem, so I don't give you the exact value of the alpha and theta, so I only tell you that, so for this gamma distribution, it will have the mean 0.14 and variance 0.0004. Okay, now and then here, so this is my initial guess at time 0. Okay, now and then here you are given that, so 2 years has gone. Okay, and I found that, so over this past 2 years, okay, so there are altogether 111 claims that I obtained. Okay, in the past 2 years. Okay, so this time, okay, so I don't give you the full information, okay, about this number of claims in each insurance policy. Okay, this time I give you the total number of claims in certain number of the insurance policy. Okay, and here you are given that, so over this in each year, okay, so we will have 310 insurance active. Okay, and then here, then together with this information, what does it mean? Okay, now so here let us try to let the N1 to be the total number of claims in 310 insurance in the first year, and N2 be the number of insurance, okay, number of claims in the 310 insurance during the second year. Okay, so here this given information means that the total number of claims, which is N1 percent 2, should be equal to 110. Okay, so here then this is what the information that you get. Okay, now then my question here is, so given this information, so I want you to obtain what is the posterior distribution for lambda. Okay, so which is this one. Okay, and then after this, so I want you to try to use this to do the future prediction. So in particular, I want you to calculate what is the probability that there will be low claim make in a particular insurance policy in the coming year. Okay, that is I want to have the probability n3 equal to 0. Okay, after you given this information. Okay, now so then how do we do this then? Okay, now so here let us try to analyze this problem a little bit. Now first of all, for part A, so our goal is we just want to get the posterior distribution of lambda. Okay, so that means, okay, so I want to get this posterior distribution given that the total number of claims in past 2 years is equal to 110. Okay, now and then here let me try to let this number to be m. Okay, so here then this is what you get. Now, so remember, how would you get your posterior distribution? So remember, we can try to use the Bayes rule, right? Okay, and then you integrate. And then you integrate from 0 to infinity. Okay. So in order to continue the game, okay, of course you have to compute these two conditional probabilities, so which is related to m. Okay, now so here then in order to get this distribution, so what you need to do is then you have to get, so what is the distribution of m. Okay, meaning, so remember m is what? The total number of claims, okay, in past 2 years. Okay, now so how do we do that? So then the first thing is, so you try to get the formula of m, so which is the common way that we can use, okay, to figure out the distribution of any random variable. Okay, now so remember here the m is the number of claims in the past 2 years, right? So that means the m can be equal to n1 plus n2. So remember, n1 is what? Is the number of claims in the first year, and n2 will be the number of claims in the second year. Okay, now and here remember in each year, so we have 310 insurance available. So that means this n1 will be what? Will be the total number of claims in the 310 insurance policy. Okay, and then here, so which is what? Equal to this one. Okay, so this one will represent what? The total number of claims in the first year. Okay, so here I guess I make a little bit typo here, so this one should be 2. Okay, so n11, n21 plus n310 1. Okay, then that will be the total number of claims in this 310 insurance during the first year. Okay, and then for n2, so again we have 310 insurance available, so that n2 will be equal to what? The total number of claims in another 310 ongoing insurance during the second year, so which is equal to that. Okay, and I guess I messed up the notation. That's still bad. Sorry. Okay, so it should be this. Now, so here, then that will be what? The number of claims during the second year. So then that will be the formula for your total number of claims in the past 2 years. Now, then the last thing is then what will be the distribution of this m there? Okay, now so here then you try to go back to the initial given condition. Now so here you are given that the number of claim in a single insurance policy follow the Poisson distribution. Okay, so that means each of these are N1, N1, N2, okay, will follow the Poisson distribution with parameter lambda. Okay, and here let's assume that all these policies are independent, then the sum of these Poisson random variable will follow the Poisson distribution as well. What is the mean? So the mean will be just 622 lambda. Okay, just the sum of all these mean, isn't it? Okay, so here then you can easily conclude that the m okay will follow the Poisson distribution with parameter 620 lambda. Okay, so then this is the one important discovery which is useful for you to calculate this probability. Okay, now then what's next? So of course the next thing will be about the parallel distribution. Okay, so here for parallel distribution, so we know it has what? It has gamma distribution, right? So which is this one. Okay, and here remember for gamma distribution, so the PDF is what is that? S over theta. Okay, and then alpha, and then S potential minus S over theta, and then divided by S gamma alpha, right? Okay, and of course in our case, so our S will be the lambda, isn't it? Okay, and here, so in order to use that to do the calculation, you have to figure out the theta and alpha, which is not something not given in the problem, right? Okay, now and here, remember how do we do this? Okay, so to do that, so we will try to make use of this fact. So remember we have the mean equal to 0.14, variance equal to 0.0004. Then we will try to use that to help us to get the alpha and theta. Okay, now so here just recall. Okay, so for gamma distribution, your second moment is equal to theta to the power k, and then gamma alpha plus k divided by gamma alpha, right? Okay, so that means, okay, so your first moment will be equal to alpha times theta, and then expected value of s squared will be equal to alpha plus 1 and then theta squared. Okay, so you can try to do the calculation by yourself. Okay, so given this, then you can get what the mean equal to 0.14, so that alpha theta equal to 0.14, and then variance equal to 0.0004. Okay, and then here variance equal to what? Second moment. Second moment minus the square of the first moment, right? Okay. Then you will get what the second equation for the alpha and theta. Okay, and here this equation looks a little bit complicated, but actually you can do a little bit simplification. So look at that. So actually this term, okay, it's just same as this, right? So that these two can be cancelled out, leaving you what alpha theta squared equal to 0.0004. Okay, now then to solve this two equation, so what you can do is you substitute the first equation to the second one. Okay, so that's so that this is what you get. Okay, so alpha theta squared equal to 0.0004, and then you take out the alpha theta equal to 0.0004, and then alpha theta equal to what? 0.14, right? Okay, then given this, then you only have the single equation for the theta, then you get this answer immediately. And similarly, the alpha will be part of automatically. Okay, now and then once you get all this, okay, then now you can go back to the posterior distribution. Okay, so remember our posterior distribution is given by this formula. And then here, then you can try to substitute the above result to this equation and then explain everything. Okay, so here, first of all, here for the first conditional probability. So remember, M follow the Poisson distribution with the mean equal to 629, right? Okay, so then this is what you get. Okay, and then on the other hand, so the parallel distribution follow the gamma distribution with parameter alpha and beta. Okay, then this will be what this portion. Okay, and then for the denominator, so that will be what just this probability multiplied by the parallel distribution, and then you integrate from 0 to infinity. Okay, and then after you put in all this, okay, so then you can start to do some algebra. Okay, now so here, even though I know the values of the alpha and beta, so I don't do the substitution at this moment because I just don't want to have too many complicated stuff flowing at one. Okay, so here, so I just do, so here, okay, then I've tried to do some algebra. Now, first of all, this gamma alpha can be cancelled out, okay, because they are common factor and which is independent of alpha. Of course, a theta, theta to the power alpha can be cancelled as well. 110 factorial can also be cancelled out, so that this parallel distribution can be simplified into this. Okay, and then again, so what you need to do is try to compute the integral in the denominator. So again, so you can see that this integral is of the forms of lambda to the power some power and then exponential minus lambda, right? Okay, so which is something rather close to the gamma function. Okay, so here what I'm going to do is just like what we did before. So we will try to use the substitution and try to turn this integral into the gamma function. So then what you do is you try to let this expression evaluate by a single variable. Okay, so that you have after the substitution, so that will be equal to exponential to the power minus y. Okay, now so here, okay, just applying this substitution, okay, and after some algebra, so you can try to turn this integral into this form, and you can see, so this one is just equal to what gamma of 110 plus alpha, isn't it? So according to the definition, so here then this is what you get. Okay, now and then here so then this will be what your posterior distribution. Okay, now and then of course you can try to do something more. Okay, so here let us try to rearrange this posterior distribution into this form. Okay, and of course some of you may say, so why do we do that in this way then? Okay, so here by writing into this form, and then let us take this number in gold as alpha prime, and then the number in blue, okay, I mean this one, by this theta prime. Okay, now so in that cases, so your PDF can be written as let's see, lambda alpha prime minus 1 exponential minus lambda over theta prime divided by theta prime to the power alpha prime. Okay, so this one also equal to alpha prime, and then lambda alpha prime. Okay, or maybe you can try to write one step forward, then you will, this is what you get. Okay. So actually this one looks like what? Looks like a gamma distribution. Isn't it? So you just treat the lambda to be your S. Okay, then essentially this is just PDF gamma distribution. So that means the posterior distribution of lambda is has a gamma distribution with the parameter alpha prime equal to 110 plus alpha, which is equal to 159. And then theta prime will be equal to 620 plus 1 over theta to the power minus 1. Okay, and then if you take theta equal to 1 over 350, so this theta prime will be equal to 1 over 970. Okay, so actually the number here is not that important, but perhaps one interesting thing is so you can see. Okay, so after the information updating, so the posterior distribution still has what? The gamma distribution, so which is same as well the pillar distribution. Okay, so remember for this lambda, the pillar distribution also has gamma distribution, and then we see that the posterior distribution is also gamma. Okay, just with little different parameter value. Okay, now so here, okay, then this is how do we get the posterior distribution. So under this scenario that you have what the partial information. Okay, and I would say here actually when you handle this kind of handle the cases, okay, where your observation is sort of incomplete. Okay, so like in these cases, so I didn't tell you the exact number of the claim in each of the insurers, so I only give you the total number of claim. So here to describe this posterior distribution, so what you need to do is just what replace this given event by what you observe. Okay, just like what we did for the maximum likelihood method for the incomplete data. Okay, so you just consider what you see, okay, and try to get the likelihood, and that's all. Okay. And other than that, okay, so other thing will be very similar. Okay, now and then here, so this is the part A about getting the posterior distribution. Now, and then the second things that I want you to do is, so here I also want you to do some future prediction. So given the data in the past 2 years, so I want to know, so what is the probability that there will be low claim made in the randomly selected insurance policy in the coming year. Okay, now so here in order to do this, okay, so of course formally you can try to use the law of total probability, right? And try to compute this as well. And then the pillar distribution. Posterior distribution. Okay, so then this is a general format that we use, okay, to calculate this probability. Now, of course, this is the traditional way of doing that. Of course, as long as you know how to evaluate this integral, so of course you can get the final answer. But just like here, instead of calculating this integral directly, so I will try to take the shortcut. Now, so here, remember, so the n, follow the Poisson distribution, right? With parameter lambda. And here in our cases, so the lambda, the posterior distribution, so actually it follows the gamma distribution. So remember, okay, in topic 2, when we discuss about the claim frequency, so actually this combination, okay, so n follow the Poisson distribution, parameter follow the gamma distribution. So actually this will imply that, so the n will follow the negative binomial distribution, and then with the R equal to the alpha in your gamma distribution, and then beta equal to theta in your gamma distribution. And here, because we are working on the posterior distribution, so that the alpha should be alpha prime, theta should be theta prime. Okay, and here in the early example, so we already get this two value already. Okay, so here given this, then you will get the R and the theta prime. Okay, so once you have this, okay, so you can now use the given table, and so the table, and try to check the PDF of your negative binomial and get the final answer. Okay, so I guess that this is just a kind of accounting exercise, so I will just leave you to do it carefully by yourself. So you'll find that the final answer will be around 84.89%. Okay, as your final probability. Okay, so here then this is the example 36. Okay, now so here before I move on to the new session, so let us try to look at one harder example, so which is example 37. So again, in this example, so what we are encountering will be the incomplete data again. Okay, so again, in this problem, so we will try to consider the case when the observation that we have may contain some censored data, which is one type of the incomplete data, right? Okay, now then the story is something like that. So here in this example, so we try to consider the loss amount in a single claim event in an insurance policy, and then for this loss amount, so it follows certain distribution with the PDF equal to this. And here, so I guess I missed something, so the S should be greater than 100. Okay, so that the sum to probability will be equal to 1. Okay, so I guess I missed this important information. Sorry about that. For S greater than 100. Okay, now anyway, so then this is the basic setup. And again, for this PDF, so we have the parameter alpha, and in this problem, so we will assume that so this alpha will be a random variable which has the pilot distribution, which is a gamma distribution with alpha equal to 2 and theta equal to 1. Okay, so this is my initial guess on the distribution of alpha. And here, let's suppose 1 year has passed. Okay, then of course, so for this insurance company, so he can try to update his guess on this distribution of alpha by looking at the loss amount that he can observe in the past. Okay, and let's suppose that in the past year, so there are altogether 10 claim payment. Okay, that made by the insurance company. And the amounts will be given as follow. Okay, so we have so this 10 number refer to the amount of the payment paid by the insurance company. And here, just be careful that so this 10 amount is just your claim payment, the payment made by the insurance company. Okay, so this is not a loss amount. Okay, just be a little bit careful on this. Okay, now and here, so let's assume that okay, so this policy has the policy limit 200 and no deductible. Okay, no ordinary deductible, no franchise deductible, and also local insurance as well. Okay, then my question is, so given this observation, so how do we determine the posterior distribution of alpha? Okay, now so here, okay, in this problem, okay, so we have 10 data that are available. Okay, now and here, because this parameter alpha is related to the loss amount in a single claim event. Okay, so here then what you need to do is, so you first try to obtain so among this n data. Okay, so what will be the corresponding loss amount as well as n? Okay, for in this 10 claim event. Okay, now and then here to do this, so first of all, because you have low deductible, okay, and no co-insurance, so you only have the policy limit, right? Okay, so here then what does it mean? So remember that under the policy limit, okay, then if your claim payment, okay, is greater than 200, okay, so which means the loss amount greater than 200, then the claim payment will be 200. Okay, and then otherwise, if the loss amount is less than 200, okay, then your payment will be just equal to S, isn't it? Okay, so here low deductible, low co-insurance. Okay, so that the loss amount just equal to the claim payment. Okay, now and then given this relation, so you can now try to get the corresponding loss amount from this end claim payment. Okay, now so here let me just write that down. So this is the background is the claim payment. Now then I try to get the corresponding loss amount. Okay, so for the first one, because this is less than 200, so this one will be your loss amount, right? And this one is 132 as 41, 107, 133. Okay, now but here, okay, for the sixth one, so the claim payment is 200. Now, so according to this figure, so any loss greater than 200 will lead to the payment 200, isn't it? So that means for this claim payment, so the corresponding loss amount will be greater or equal to 200. Okay, and then for the last four, so that will be 126, 104, 145, and then the last one again, so you have 200, right? So that will be greater or equal to 200. Okay, so here then that will be the corresponding loss amount, okay, in this 10 claim event. And we can see that, so here among this data, so we have two of them, okay, which is what a wide censored data, isn't it? Okay, and then other 8, okay, will be what? Will be a complete data. Okay, you know the exact value. Is that okay? Now, so here again, that we are running into the situation that, so the observation on the loss amount is a incomplete data, in the sense that it is the data is wide censored at 200. Okay, now, so given this incomplete data, so how would you get your posterior distribution? So again, I would say the derivation is just similar to the case for the complete data, except that, okay, so this given event, okay, will be replaced by what you observe. Okay, so that means your posterior distribution, okay, should be something like this. So will be given that, so S1 equal to 125, and then S2 equal to 132, S3 equal to 141, S4 equal to 107, S5 equal to 133, and then S6 equal to greater than 200, S7 equal to 126, and then S8 equal to 104, S9 equal to 149, and then S10 greater or equal to 200. Okay, so then this is what this probability is about. Okay, so then you take this event to be B. Okay, then here, then you can calculate this probability via this formula. Okay, so then that will be the probability that, okay, so B will happen. Okay, given that you have alpha and then pi. Alpha divided by, you integrate this from 0 to infinity. Okay, so then this is what you do. So actually what you need to do is just what to obtain this probability. Okay, now so how do we get this then? Okay, now so here to facilitate the presentation, so I will try to rearrange the data a little bit. Okay, so in particular here, I will try to put this two censored data to the last two entry. Okay, so that's here I will try to arrange the data. arrange the data like this. Okay, let me see. So S6 will become 126, S7 equal to 104, S8 equal to 145. Okay, so I put these 8 complete data in the front, and then the last 2 will be on the last page. Okay, now and then here, so given this, so you can now try to compute this probability of this event given the alpha. Okay, now so here for the first 8 event, okay, then that will correspond to this probability. Okay, you know the exact value for that. Okay, and then for the last 2 censored data, so meaning that the loss amount greater or equal to 2000, then the probability will be equal to this. Okay, now and then here, given that, okay, so your f follow this has this PDF, okay, then you can just put that in. Okay, and you can put that in. Okay, so for the first 8 data, so you just put in the PDF directly. Okay, and then for the last 2 censored data, so we are asking for the probability that SJ greater or equal to 200. So that means it will become a integral. Okay, and then that will be power 2. Okay, now and here, then you just try to evaluate this integral carefully. So which is equal to which is equal to 100 divided by s to the power alpha, and then you make from 200 to infinity. Okay, so then that will be equal to something like this. Okay, now then here, then we get this f. Okay, so which is these 2 important things. Okay, and of course for the pilot distribution of alpha, so here we know, so it follow the gamma distribution with this alpha equal to 2, theta equal to 1. Of course you can also get it as well. Okay, so pi alpha, okay, will be equal to alpha over theta to the power alpha prime. Okay, so remember, okay, the s will be replaced by alpha in your gamma distribution, and then that will be exponential mass alpha over theta divided by theta. Sorry, no, theta is alpha. Okay, and then gamma alpha prime. Okay, just be careful here. So the alpha here represent the s in your distribution function. Okay, now anyway, so that this is your polar distribution. Then basically then we have almost everything done. Okay, but here, okay, then in order to get your posterior distribution, so what you need to get will be this integral. Okay, so you have to get this. Okay, and I would say this will be a little bit challenging this time. Okay, so why it is so? So let me try to write down this integral for you. Okay, then you will see why. Okay, so let me erase that. Okay, now, so let me focus on this integral. Okay, now then let me put in the stuff. Okay, now so then you got something like this. And then you also get your gamma function, this one. Okay, That's tiring. Okay, of course here you can try to punch in the alpha prime and theta, so which is alpha prime equal to 2, theta equal to 1. Okay, so you can also do the substitution as well if you don't want to have so many letters. Okay, let's do the patience here. One, and then 2, and then 2. Okay, now and then so then you need to evaluate this integral. Okay, of course here you can try to do a little bit simplification. Okay, so this one will become the alpha and the exponential minus alpha, something like that. Okay, and gamma 2 equal to 1, right? So then this is what you get. Now, but there is a little bit trouble. Okay, now so here in order to complete the game, so then you have to evaluate this integral. Okay, but here you can see for this integral, so you can see this is very complicated. Okay, now first of all, it involves alpha to the power something. Okay, and you have exponential to the power minus alpha. Okay, and then of course let's say if you only have these two terms unknown along here, then you can try to get this integral by using the this gamma function, right? Isn't it? But unfortunately here, so it looks like that this is not just the term involving the alpha. So it looks like this term and also this term is also involve the term alpha. Okay, and here this two term, okay, actually is in the forms of some constant to the power alpha. Okay, so the things is complicated, right? Okay, so here so it looks like that with this additional term, it looks like that we cannot use this gamma function trick to derive this integral. Now, so here it seems like that the gamma function is the only asset to calculate this integral, isn't it? So here, in order to resolve this problem, what I'm going to do is I will try to transform this integral into the forms of exponential to the power something to the power alpha. Okay, so one way is you try to write that into exponential to the power natural log c. Okay, so remember this is equal to alpha, right? Sorry, equal to c, and then to the power alpha, and then you will measure that, so you get something like this. Okay, then by doing that, then you can now rewrite these two terms, okay, in the forms of exponential to the power something to the power something times alpha. Okay, so that you can still transform the whole integral into the forms of alpha to the power something and the exponential minus something times alpha. Then you can derive this integral using the gamma function. Okay, so that's why here what I'm going to do is so will be the following. So here, okay, because these two terms, okay, these two terms appear in your this function f, isn't it? Okay, so here, okay, then at this point, okay, when you get this f, so what I'm going to do is, so I will try to rewrite these two terms, okay, into this exponential function. Okay, so I do it one by one. Okay, so you use c to the power alpha equal to exponential alpha natural log c. Okay, and try to change these two into these two things. Okay, now and then after this, so by some and then here you can substitute the values of si, which is your this h complete data. Okay, and then you put that in and do a little bit calculation. Okay, then you will find that so the f will be equal to this number. Okay, so which is in the forms of alpha to the power something exponential minus to the power something. Okay, and then given this, then you can now combine with this PDF of the gamma distribution, and then you can rewrite this integral successfully. Okay, so here then this is what we do. Okay, so here, okay, first of all, so for pilot distribution, so that will be of alpha will be equal to that. Okay, alpha times its potential minus alpha. Okay, so which is something that we have here. Okay, then given this, then now you can try to substitute all this in this integral. Okay, of course you can also do the same for the numerator as well. Okay, now and then here after you do this treatment, then you can see this integral will be something in forms of alpha to the power something and then its potential minus something times alpha. Okay, now and here in order to evaluate this integral, so first of all you can first take out this constant. Okay, so take that out. Okay, and here for the remaining time, so that will be something like this, right? So you use the substitution. Okay, take the y equal to this number and try to transform this integral into the form which match the gamma function. Okay, and then once you have that, okay, so you can see, so this integral is just what the gamma function, which is gamma tan. Okay, and here then actually we evaluate this integral successfully already. Now then to evaluate this gamma function, so remember gamma of alpha plus 1 equal to alpha times gamma of alpha. Okay, then you use that, then you start from gamma 10, then that will be equal to 9 gamma 9, and then you apply one more time, so it's gamma 8. Okay, and then 9 times 8 times 7 gamma 7. Okay, then you just keep on paying this until you reach 1. Okay, and remember gamma 1 will be equal to 1, right? So that this guy will be equal to 9 factorial. Okay, so which is the one that I get here. Okay, now and here if so that will be what your Pilot distribution. Okay, sorry, I'm the posterior distribution. Okay, and then here if you try to look at this function, okay, so actually by some rearrangement, you can show that so this posterior distribution actually is just a gamma distribution with this alpha prime equal to 10 and theta prime equal to this number. Okay, so here I'm not going to really do the derivation, so you can just compare by yourself. Okay, now so here then this is how do you get the posterior distribution of for the incomplete data. So again, so the trick is just so when you calculate your posterior distribution, okay, so in this step, so when you calculate the likelihood that of getting this data, okay, then here then you just replace this event by something that you observe, and then here like in our cases, so if you have complete data, then you just use PDF. Otherwise, okay, if you have the white center data, which you can only tell the range of the SI, then you just replace by this probability, as simple as that. Okay, so here then this is how do you get the posterior distribution. Now and then here let us try to do something more. And here what I want you to do is, so I want you to obtain what is the predictive distribution of S. So that means we want to find the new distribution of this S based on your new guess on the values of alpha. Okay, and I would say that actually this is just a piece of cake. Okay, so here, okay, to get this predictive distribution, okay, so again you try to use the law of total probability and try to do the job. And then here, okay, so this should be the S. Okay, then this is the formula that we should use. Okay, so just consider all possible values of alpha, and then you multiply the PDF of S, and then by this updated distribution, the posterior distribution. Okay, now and then here, so once you got this, okay, then you just punch in the PDF as well as your posterior distribution. Okay, something that you get it in the earlier session. Now then again, so you need to evaluate this integral. Okay, and then again, so you can see that this integral consists of the term alpha to the power something, okay, and then exponential to the power minus something times alpha, so which is the second term here. And what's more, you also have the term which appear in the numerator and denominator, okay, so which is what, something like some power to the alpha. Alright, now so remember here, in order to derive this integral, so according to our early experience, so we will try to make use of the gamma function trick to do the job. Okay, but of course here it seems like that then you need to try to do something to try to get rid of this term. Okay, so remember one solution that you can do is you try to change it into this exponential to the power natural log C. So this is the trick that we always use to resolve this problem. Okay, so again so we have two, so you have two terms involved having this problem, right? This one and this one. Then you just use this fact and try to transform these two terms into these two. Okay, and then immediately then you will get with, then you can try to eliminate this term, okay, from your integral, so that your integral will be something similar to the gamma function. Okay, now so here after you do this changing, okay, so then as well try to take out something all irrelevant of alpha. Okay, so you take out the all this, okay, and this is the term that you need to entertain. Okay, so again, which is equal to alpha to the power something and the exponential minus power something. Okay, then again, so this integral you can get the value by using the gamma function. And again, then we try to use the change of variable, so we let the u equal to this number, okay, so that you can turn this into a single term like that. Okay, so which match the term in your gamma function. Okay, and then here because the term is a little bit messy, just try to do the calculation carefully, and this is basically what you get. Okay, now and then here after you have this, then this term will be just equal to gamma 11. Okay, and remember to evaluate this, so you can use this use this fact and try to help you to do the job. So then this will imply the gamma 11 equal to 10 factorial. Okay, so here then you just, so given this, then you just put that in, and then I guess there's no way to do any simplification. So here then I will just leave the answer like this. Then that will be what? The predictive distribution of S, which is calculated based on the updated guess on the values of alpha. Okay, so here, okay, then these are the example about the Bayesian estimation. So given the data, then how do you do the updating on the distribution of the unknown parameter? So here, basically we finished the first part of the Bayesian estimation, and then next time, so we will try to discuss other aspect related to the Bayesian estimation. So that's all for today, and have a nice day.